All right, moving on to reactions in aqueous solution. We're going to learn how to write different types of equations for chemical reactions. And then we'll also get into some naming and formula writing as well today. So let's look at this example. Magnesium metal is placed in a solution of silver acetate. So this is a single replacement reaction. We'll learn officially about that later on in our lesson. There's different equations we can write. Let's start off with the formula units or molecular equation. This shows the complete formulas of all the substances involved in the reaction. So this is probably what you typically think of with a chemical equation. So let's go ahead and write this equation. So here's our unbalanced chemical equation. We want to also include states of matter for each substance. And then we need to balance this equation. That's a mess up there. I guess that should be Ag there in the end, silver. And so here is our complete chemical equation for the reaction. Formula units for dealing with ionic compounds, molecular equation if we're dealing with molecular compounds. We can also write what's called an ionic equation. And in an ionic equation, formulas are written to show the predominant form. I stress that word predominant. Predominant form that each substance takes in aqueous solution. So let's take a look at that. So here is our ionic equation. Now here's the deal with ionic equations. You can either balance from the original equation or just balance at the end. Now technically, especially if it's a redox reaction such as this one, you want to balance it from the original equation. We do have those some spectator ions, and it doesn't really matter if we have a coefficient for them or not. So I'm going to balance it. So here it is, balance at the end. And then let me also balance it from the original equation. Since we had two silver acetates, we're going to put a 2 in front of each the silver ion and acetate. Notice for those ions, we label them both as aqueous. In fact, the only place that we find ions are in solution. So you can't put any other state of matter. So Ag plus can't be solid. It's not solid silver. It's silver ions. They are in solution. On the right side, we got to balance the acetate because we had magnesium acetate, which from the original equation had 2 acetates. And then 2 silvers. Take it a step further, we write our net ionic equation. In fact, on most end of the year exams, such as the AP or IB exam, most often they're looking for the net ionic equation. And so this shows all the substances that are involved in the reaction, and it does not show those substances that are not involved or do not participate in the reaction. We call those spectator ions. So looking at the ionic equation, we have a single replacement reaction, so we have 1 spectator ion. What is the spectator ion? Remember how to identify those. They are the same after the reaction as they were before the reaction. So our spectator ion is acetate. We have acetate in solution before the reaction. We have acetate in solution after the reaction. What did the acetate do during the reaction? Absolutely nothing. So let's get rid of that and let's write the net ionic equation. So again, notice if we carry the coefficients from the original molecular or formula unit equation, not only will mass balance, but charge will balance as well, and that's what we want for redox equations. We'll learn more about that later on. So in this case, right now, either way is fine. Balancing with all 1s or 1, 2, 1, 2 is fine as well. Please, please, please refer to table 4.9 on page 130. It shows some very important information, especially the weak acids and weak bases. So remember, weak acids and weak bases are partially ionized. Only part of them break apart into ions. Most of it stays unionized. And so when we're representing weak acids or weak bases in an ionic or net ionic equation, the predominant form is the unionized substance. Likewise, we see some examples of insoluble salts. Of course, we want to show those as associated, which is the opposite I call of dissociated. We do not want to show insoluble salts as dissociated because they exist as a solid and not as aqueous ions. Also, page 131, problem-solving tip to help you keep track of everything. And again, talks about strong acids and bases versus weak acids and bases. So speaking of redox reactions, which we'll focus on in depth later on in the year, oxidation numbers or oxidation states. We use oxidation states to determine what is being oxidized and what is being reduced in a redox reaction. So an oxidation number or oxidation state refers to the charge of the individual atoms in an element or as ions or in a compound. The rules are found on page 132, so make sure you familiarize yourselves with those. In table 410, also we see some more examples and some more rules, so take a look there as well. Let's do some together just to refresh your memory. Go to page 133, example 4-4. It says, determine the oxidation numbers of nitrogen in the following species. Let me write these up for you. So if you take a look at the rules, oxygen has the same oxidation state in most of its compounds or ions. So oxygen has an oxidation state of -2. So in N2O4, we have 4 -2s, which need to be balanced with 2 nitrogens. So we have to determine the oxidation state of each nitrogen. We treat it just like we do with charges, but keep in mind, where charges represent something real, we have a different number of protons versus electrons. Oxidation states don't represent anything real. It's just to help us keep track of what's being oxidized, what's being reduced in a redox reaction. So in this compound, dinitrogen tetroxide, each nitrogen has an oxidation state of +4. There's another rule for hydrogen in a compound or ion, polyatomic ion. Hydrogen in most compounds or ions has an oxidation state of +1. What I failed to mention on the previous example too is that the sum of the oxidation states is equal to the charge of that particle. So in N2O4, that's a neutral molecule. So the oxidation states are going to add up to 0. Likewise here, ammonia, neutral molecule. We have nitrogen plus +3. Again, each hydrogen is +1 is equal to 0. So in this case, nitrogen is -3. So for that next one there, hydrogen is +1, each oxygen is -2, plus the nitrogen. All of that has to add up to 0. So in this case, nitrogen is +5. Nitrates. This time the oxidation states are going to add up to the charge, in this case, which is -1. So nitrogen plus -6 equals -1. So that means that nitrogen is +5. And lastly, atoms of an element, any element, whether it's diatomic or not, have an oxidation state that is 0. So go ahead and try the exercise on page 160. Just do 42A. Pause the video, work on that, and I will give you some answers. All right, there's a lot of them. Let me list them for you, and I'm just going to go in order. +3, +5, +5, +5, +3, +5, +5, +5. So hopefully you got all of those. If you have any questions on them, let me know. We can go over them in class. So we've already done a little bit of naming and formula writing. We'll do a little bit more here just to reinforce it, especially leading into writing chemical equations. So we'll start with some nomenclature, starting with molecular compounds. Remember, a molecular compound consists of two or more non-metal atoms that are bonded together. This will be covalently bonded, as we'll learn later on in the year. When we name molecular compounds, what should come to mind is this, prefixes. So every time we name a molecular compound, we're going to use prefixes like mono and di and tri and tetra and penta. And these prefixes are used to denote the quantity of each of the nonmetal atoms present in that compound. Something else that's important with the names of molecular compounds is that they all end in the suffix "ide." So let's look at some examples. So this is the one you should definitely think of anytime you think of writing a formula or naming a molecular compound. You probably learned the name of this before you even took chemistry, even before Chem 1. So this is notice that if there's just one of the first element in the formula, we don't use a prefix mono. We just call that carbon and then dioxide. In fact, it's common practice, even if the second element there's just one, to not use a prefix mono, but usually I do. So here's an example of that. And recall from Chem 1, if your prefix ends in an O or an A, and that precedes a vowel in the name of the second element in the compound, we drop the O or A from the prefix. So this is not carbon monoxide. Drop the O from mono, carbon monoxide. Let's take a look at another. So again, we just have one of the first element, so we don't need a prefix, just sulfur, the whole name of the first element. Prefix for 6 is hexa. And we have F, fluorine. Take off the ene from fluorine and add ide, fluoride. So we're going to take off the last syllable or last two syllables of the second element's name and then add the suffix ide. Take a look at some more. So this time we have more than one of the first elements, so we will definitely use a prefix. We have 2 arsenics. Five, prefix for 5 is penta. So again, we'll take off the A from penta, make pent oxide, diarsenic, pentoxide. Next are ionic compounds. Ionic compounds consist of cations and anions bonded together. Technically, this is ionically bonded together. Usually, they consist of a metal combined with a nonmetal, but that's not always the case, so be careful. It's always cations with anions. Often, the cation comes from a metal. The anion comes from a nonmetal. For naming ionic compounds, never, ever, ever use prefixes like we do in molecular compounds. No prefixes ever with ionic compounds. In naming ionic compounds, they all end in ide, except for those who have an anion that is a polyatomic ion. So all monatomic anions end in ide, like oxide, fluoride, bromide, selenide, nitride. But if the anion is polyatomic, then we just take the name of the polyatomic anion. There are, as you know, metals that can form more than one possible charge. For these, we can use a stock system, which involves using Roman numerals. And the Roman numeral tells us the size of the charge. And then, of course, the other way to name these ions is by using the old system, which uses the older Latin name. And again, we talked about this before. The suffix we use depends on the higher charge versus lower charge of that particular ion. Or oxidation state, since we learned about oxidation numbers. So the ion with the lower oxidation state is given the us suffix. And then the ion with the higher oxidation state is given the ic suffix. So again, you should have these already memorized. We have the ions of copper, iron, tin, and lead. So Cu plus 1, by the way, is called cuprous. Cu plus 2 is called cupric, or copper 1 and copper 2, respectively. Let's add one to those. Let's add the ions of mercury. So you have Hg2 plus 2 and Hg plus 2. So the Hg2 plus 2, the oxidation state is plus 1. That's the lower oxidation state. So that's called mercurous. And then Hg plus 2 is called mercuric. All right, as I mentioned before, I was going to add to the list of polyatomic ions you need to memorize. So again, memorize the 10 I've given you already. And let me give you a few more to memorize. So here they are. They're also listed for you in your textbook, table 411 on page 136. Let me just list the names for you here, but you can check your book too if you miss anything. CrO4 -2, that's called chromate. Cr2O7 with a -2 charge is called dichromate. Be careful the next one. It's not chromium, it's carbon. C2O4 with a -2 charge is called oxalate. You can look in the book for spelling on oxalate. PO4 -3 is phosphate, so PO3 -3 is called phosphite. We have hydronium, nitrite, HCl3, that's called either hydrogen carbonate or better yet, bicarbonate. Let's start with the chlorine one. So we have 4 different chlorine polyatomic ions. ClO3 is called chlorate. 1 more oxygen than the 8 gets a per prefix. So ClO4 minus is called perchlorate. 1 oxygen less than the 8 ion gets the ite suffix. So ClO2 minus is called chlorite. 1 less than the ite, 1 less oxygen than ite, gets the prefix hypo. So ClO minus is called hypochlorite. So again, make sure to memorize all of the polyatomic ions. And I think to save some time, we're going to skip the examples. We've done quite a few already. If you need to do more, please let me know, and we can certainly do some more. All right, next up, naming acids, acid nomenclature. There's 2 types of acids. We have binary acids and ternary acids. For binary acids, they contain the element hydrogen and 1 other nonmetal. So how we name binary acids is we use the prefix hydro. They all start with hydro. And then the second element's stem, so it's not the whole name. So the stem of the second element, and then we add the suffix ic, and then the next word is acid. So here's one you should know. So binary acid, we start with the prefix hydro. Second element is chlorine, so we'll just take off the suffix -ine. Hydrochloric acid. How about HBr? That would be hydrobromic acid. HI, hydroiodic acid. Be careful with this one. This is binary, so we got to start with the prefix hydro. It doesn't matter that there's 2 hydrogens. Still name it the same way. Hydro, this time it's the whole name of the second element. Hydrosulfuric acid. So it's not hydrosulfic. Don't take off the ic. Hydrosulfuric acid. Not to be confused with sulfuric acid. How about that one? Hydrosalinic acid. All right, ternary acids, also known as oxoacids. These are acids that contain an oxygen-containing polyatomic ion along with, of course, hydrogen. Here's how it works. The 8 ions become ic acids. If you ate an acid, what would it taste like? It would taste icky. 8 ions become ic acids. Ite ions become us acids. Here's some examples. What is the polyatomic ion in this acid? That is nitrate. So HNO3 is called nitric acid. A polyatomic ion in this acid is nitrite. So this is called nitrous acid. Again, doesn't matter that there's 2 hydrogens. Sulfate, so H2SO4 is called sulfuric acid. All right, that's H2SO3 is sulfurous acid. This acid contains carbonate, so this is called carbonic acid. This contains phosphates. This is called phosphoric acid. Probably not the best way to write this formula, as we'll see later on in the year, but it's okay for now. This acid contains oxalate. This is called oxalic acid. I've talked a little bit about redox reactions, so here officially are the notes on redox reactions. Redox, of course, is short for oxidation and reduction. These are reactions where electrons are transferred, and the oxidation state or oxidation number for one or usually two elements in the reaction changes. Sometimes just it's one substance, but usually two. So be careful with the terminology. Reduction describes a process where electrons are gained. That's called reduction because the oxidation state for that substance decreases. It is reduced. Conversely, oxidation describes a process where electrons are lost. The oxidation state for the substance that is being oxidized increases. So maybe remember this to help you. Leo says grr. Losing electrons is oxidation. Gaining electrons is reduction. Also be careful of these terms. Oxidizing agent. The substance that causes another substance, something else, to be oxidized, while at the same time that substance is reduced. So this is an oxidizing agent. Likewise, a substance that causes something else to gain electrons is called a reducing agent. And that substance, the reducing agent, because it is causing something else to gain electrons, is losing electrons. It is oxidized. So we use these terms for the reactants of a redox reaction. We have oxidizing agent and reducing agent. Little notes here. Nonmetals in odd-numbered periodic groups favor odd oxidation states, and those in even-numbered groups favor even oxidation states. Also important, the maximum oxidation number for a representative element or main group element is equal to its periodic group number. And I'm talking about the naming or the numbering system 1A, 2A, group 13 is 3A, group 14 is 4A. So it's those numbers. Take a look on page 141. So asking to see if this is a redox reaction or not. So the first one there is definitely a redox reaction. It's a single replacement reaction. Let me show you how we determine that. All right, so let's determine the oxidation states of each substance in the reactants and compare it to the products. Now, since we have nitrates in the reactants and the products, I know that neither the nitrogen nor oxygen is being oxidized or reduced. So let's look at the other things. In silver nitrate, what is the oxidation state of silver? Well, it's a monatomic ion, so its oxidation state is the same as its charge. I'm just going to indicate that above the symbol. Copper, elemental copper, 0. In the product side, we have copper in a compound. Again, this is a monatomic ion, has a charge of +2, therefore its oxidation state is +2. And then we have elemental silver that is produced. So we see the silver is going from +1 to 0. That means the silver ions are being reduced, so Ag+ is being reduced. Copper is going from 0 to +2. Its oxidation state is going up, telling us that copper metal is being oxidized. Go ahead and work on number 69 on page 161. Go ahead and do all parts. Actually, no. Let's do A and C only. I don't think we need to do all of them. A and C. Identify it as a redox reaction or not. If it is a redox reaction, identify the substance being oxidized and the substance being reduced. Go ahead and pause the video. A and C only. So both are redox reactions. In letter A, zinc is being oxidized. And CO plus 3, cobalt 3. Can't just put CO. CO plus 3 is being reduced. In letter C, chlorine is being oxidized. And nitrogen is being reduced. All right, number 73. Let's again just do A and C. This time we're going to write out both the ionic and net ionic equations. So you're given the formula unit or molecular equation, write the ionic equation, write the net ionic equation, and see if you can determine what is being oxidized and what is being reduced. Go ahead and pause the video. So go ahead and compare. Number 73A, I balanced both mass and charge. And so in this reaction, the iron is being oxidized. It's going from 0 to +2 oxidation state. The hydrogen ions, H+, is being reduced. We're going from H+ to H2. In this reaction, chloride ion is a spectator ion, so we do not show it in the net ionic equation. In letter C, I did not balance this from the original equation, so only mass is balanced, charge is not balanced. And so in this reaction, the zinc is being oxidized. It's going from 0 oxidation state to +2. The H+ is being reduced. It is going from +1. I take that back. The hydrogen is not being reduced. Hydrogen goes from +1 to +1. It stays +1. But we have the nitrogen that is being reduced. So in nitrates, nitrogen's oxidation state is +5. In ammonium, on the right side, nitrogen's oxidation state is +3. Make that -3. So we go from +5 to -3. The nitrogen is being reduced. That concludes this lesson. Next time we will talk about the different types of chemical reactions. Thanks for watching.